Hey everybody, I wanted to go over a sample problem. This is right from the Brown-LeMay 13th edition. It's chapter 17. It's question number 27. Just to draw your attention to it, let me see, it's this question right here. Okay, so we have a buffer. You want the pH of the buffer before anything is added to it, and then you're going to add a strong base, and then you're going to add a strong acid. And we want to see what's going to happen to the pH when you add the acid and find the pH after you add the base. I think it's pretty self-explanatory that whatever the pH of the buffer is, when you add the base, the pH is going to go up. When you add the acid, it's going to go down. We just want to know quantitatively how we can do that. So let's go here and let's take a look and see what we got. Okay, so for the first part of this problem, notice we're not adding anything to it. So because we're not adding anything to the solution, what we can do is just do a weak acid equilibrium problem. Okay, before we get started, I do want you to know that you'd have to be given the Ka 1.8 times 10 to the minus 5. Okay, and so once you have that Ka, we can do the pH. So if we're not adding anything to it, and this is a weak component, weak acid, weak base problem, then it's just write the reaction, do the equilibrium. I say just like it's that easy, but it's not necessarily that easy, but that's what it is. Okay, when you're trying to look at these problems and you're trying to get in the right frame of mind, okay, nothing's being added to it. This is a mixture of just a weak acid and its conjugate, so it becomes just a weak acid problem. So we write the weak acid reaction, HC2H3O2 plus H2O is in equilibrium with H3O plus C2H3O2 minus. Okay, do an ICE chart. Okay, now ICE charts have to be done in molarity, so it's per 1 liter, so that's good. So that makes the math a little easier. So this is 0.1 molar. Water doesn't matter. H3O is 0, and now we have this 0.13 moles of sodium acetate. That's our source of the acetate ion, the conjugate. Okay, per 1 liter, so that means the molarity is 0.13. So it shifts to the right because there's a 0 over here, so this is going to be minus x, it's going to be minus x, and we get 0.1 minus x, and 0.13 plus x. Now, we set up our Ka. So Ka equals 1.8 times 10 to the minus 5, which also equals products over reactants. X times 0.13 plus x all over 0.1 minus x. Okay, so now when we do this, we can get rid of these guys, okay, because we assume that they're small. And so now we do 1.8 times 10 to the minus 5 times 0.1 divided by 0.13. Okay, and so I multiplied by 0.1 and divided by 0.13, and so you get 1.38 times 10 to the minus 5. Don't forget the times 10 to the minus 5 that's over here. Okay, that is a thing to not remember, or it's something that people don't remember. Just make sure that you know that it's there. That equals x, which also equals the hydronium ion concentration. Okay, that equals the hydronium ion concentration. Okay, well now we just have to do the pH. pH equals the negative log of the concentration of H3O plus, and then we do the negative log in our calculator of that, and we get a pH equal to 4.86. Okay? So the second part of this problem is where we take that same solution and we add now a strong base. Okay? Now, this is where we have to worry about the titration, or just the additions part of stuff. Okay? So by adding the strong base, the pH is obviously going to increase, but we want to know by how much. Well, in order to do this problem, okay, we have to do it in two steps. We have to do the stoich step, the stoichiometry step, followed by the equilibrium step, because we have that context clue that we're adding something to the buffer. Okay, so what do we do? Okay, well, this is a base. Okay, it's a strong base. It completely ionizes. It's on the list of strong bases. So we know that the strong base is going to be there. So a base reacts with the acid. Now we have a choice back here. We either are going to react with this or this. Which one is the acid? This guy is the acid. Okay? So that's going to react with HC2H3O2, and that is going to react with, it's not an equilibrium really, okay, with, okay, and then it becomes H2O plus C2H3O2 minus. Okay, and so this is how a buffer works. This at 0.02 moles, and this at 0.1 moles, and this at 0.13 moles. All of these things now, this gets us to a new ratio of the acid to the conjugate, but also this is why this solution is a buffer, is because at the end of this is going to be all zero. Okay, watch how this becomes all zero. Well, where's the limiting reactant? This guy is the limiting reactant. It's not an equilibrium problem, so we have reactants and products. Okay, and so that's why we know the acid reacts with the base. The acid reacts with the base. If we have a strong base, it's going to react with the acid. Okay, so anyways, this is our limiting reactant. So by definition, the limiting reactant gets used all up, so that's going to be 0. And this is going to be minus 0.20. And so now that's 0.08. And now this is going to be plus 0.02. And so that's 0.15. Okay. And so that tells us now how much after the initial addition of hydroxide, now what this new ratio, or how much the ratio is of the weak acid to its conjugate. When the ratio of the weak acid to its conjugate changes, the pH will change. But notice it's not going to change by much because there is no weak or strong base. So it's only going to change by a little bit. Okay, and I get it, a little bit is relative, but nonetheless, it's still going to change, not as much if we just added strong base to water. So now we've done the stoichiometry to find out how much is going to reach equilibrium. So now we do the equilibrium step. The equilibrium step is going to entail us writing an equilibrium acid reaction. C2H3O2 minus. Okay, and these values that we got here are the initial values that go into our ICE chart. Okay, so again, water doesn't matter. How much acid do we have? We have 0.08. Oh, now we need it to be in molarity, right? So remember, there's 1 liter of solution. So again, that makes our math a little easier. Okay, so 0.08 divided by 1 is 0.08. This is 0, and this is 0.15. Okay, because 0.15 moles divided by 1 liter gives us 0.15 molar. Okay, so now we don't know how much is at equilibrium, because equilibrium, we don't use up everything. So now it's bouncing back and forth between this and this getting created. Okay, so it's going back and forth, back and forth, back and forth, back and forth. And so, but we know that it's going to shift kind of in this direction because we have none of this. So we're going to subtract here, add this, add this. So it's 0.08 minus x. This is x, and this is 0.15 plus x. Okay, so now we do a Ka problem. Times 10 to the minus 5, that's our Ka, equals, okay, products, x 0.15 plus x over 0.08 minus x, and again, okay, this cancels out, and this is different because now, again, this ratio here is different, so that's going to make the pH slightly different. So we're going to plug this in the calculator. So we're going to multiply by 0.08. We're going to go times, or sorry, not times, and then we're going to divide by 0.15. And so now we get a concentration of 9.6 times 10 to the minus 6 equals x, and that is the concentration of the hydronium ion. And so now, hopefully, this pH is higher, right? We want it to be higher than what our pH was before, which was 4.86. Okay, so we're going to do the negative log. We're going to do the negative log of that answer, and we get that pH equals 5.01, and that makes sense. Okay, now the last part of this is something a little different. Now we're adding moles of a acid. Okay, now it's the same idea as the last one. Because we have this context clue of add, we know we need to do a stoich followed by an equilibrium step. Okay, so that's going to get us to the answer. Now, in order to do this, our stoichiometry step is going to be the strong acid. Let me make sure that I set this up right. HNO3 reacts with, now we have a choice, right? And now we have a strong acid. Okay, the strong acid can either react with the acid or the base. What do you think an acid is going to react with? The acid is going to react with the base now in this case. So the base is C2H3O2 minus. And when this reacts, it reacts to form C2H3O2 plus NO3 minus. So again, the strong acid here is going to be used all up, and it's going to be converted into this weak acid because it's a buffer solution. So now we do our stoichiometry step. It follows the same procedure as the last one. So we have 0.02 moles. Remember, stoichiometry is done in moles. Now, in this case, we have 0.13 moles here, because that's what it was originally, right? 0.13 moles and 0.1 moles of the acid. So just make sure you plug your numbers in the right spot. It's 0.1. And this nitrate, that doesn't matter. Okay, that's a spectator no matter what we do. Okay, now we find out which one's the limiting reactant. In the stoichiometry step, we have to pick the one that is the limiting reactant, and so that's this. So we're going to lose it all, and then this becomes 0. And so now, again, the reactant, we lose the reactant. Now here we gain the reactant, plus 0.02. So here, this goes down to 0.11, this goes up to 0.12, and now we have a new ratio of conjugate base to its acid. Okay, but it's still, now that we've added the weak acid, it's still an acid equilibrium problem once we're beyond this. So the acid equilibrium problem, again, we keep the equilibrium side the same as we've always done. We write an equilibrium reaction, okay, HC2H3O2 plus H2O is in equilibrium with H3O plus C2H3O2 minus. And we use these values up here, keeping in mind that this is in 1 liter of solution. We use these values here to get the molarity to plug into this new ICE chart. Okay, so 0.11 moles for every 1 liter here. Let me make sure that I have the right column. This is going to be 0.11. This is going to be 0.12. Water doesn't matter. This is 0. And because this is 0, we're going to shift toward the products. So that means we're going to lose X. We're going to gain X here. We're going to gain X here. So it's 0.12 minus X, and 0.11 plus X. Okay? Now we do the equilibrium expression. 1.8, well, we plug it into the equilibrium expression, times 10 to the minus 5 equals X 0.11 plus X over 0.12 minus X. Okay, so now just like every other equilibrium problem, we get rid of these, okay, and notice that this ratio is slightly different. Because it's a slightly different ratio, we get a different pH. Okay, that ratio is the thing that controls the pH. Okay, so when we do this, we get 1.8 times 10 to the minus 5 times 0.12 divided by 0.11. Okay, we get 1.96 times 10 to the minus 5. Now, that equals the hydronium ion concentration. We have the hydronium ion concentration. Okay, so now we can do the negative log of that. We do the negative log of that, and we get that the pH is equal to 4.71. Okay, and that makes sense. It's below that original starting pH. So there is a sample problem, soup to nuts. Hopefully that clears it up, and have a great day.